All right, we are back. Thank you again to the organizers for inviting me to speak. This is the second lecture. So I'm just going to remind you that in the first lecture, we discussed groups with coarsely bounded generating sets. And I mentioned Mann and Rafi's classification. Which is basically a description of which surfaces have mapping class groups with coarsely bounded generating sets, which is important because those are the ones where we can say something about their geometry. So if you don't know what this means, you should probably watch the first video. But for the purpose of this video, we can basically just take for granted that there's some meaningful sense in which we can talk about quasi-isometry types of at least some big mapping class groups. So the obvious question that leads us to, right? We have some big mapping class groups that have a well-defined coarse geometry, by which I mean metric up to quasi-isometry. So we know there are some coarse geometric properties that can be asked about such a group. So what coarse geometric properties does the mapping class group of a surface, and here I'm always assuming we're talking about infinite type surfaces. Okay, that's a very broad question. Obviously there's lots of different ways you could answer. Lots of different sort of sub-questions. Maybe a more concrete question, which will hopefully make it easier to answer some parts of question one, is well, I'll say, can we find some nice metric space which is quasi-isometric to the mapping class group of sigma. So remember, in both of these cases, right, not all surfaces have this question well defined. We're basing this on, we're only looking at the surfaces that Mann and Rafi have identified as having at least the possibility of discussing their coarse geometry in this framework. And I think that's a reasonable way to restrict ourselves, right? If you watch the first lecture, you'll see that this coarsely bounded thing is in some sense, it feels like it's the most general possible definition you could have and still get anything useful out. That's probably not true. That's how it feels. So can we find some nice metric space that has a quasi-isometry, and then hopefully you can ask about the geometric properties of this metric space, and they'll be a lot friendlier than the geometric properties of the whole mapping class group. So that's our basic setup, our basic question. So now I'm going to talk about some answers to that question. So let's look for a little while at a particular surface, which is the plane minus a Cantor set. This is sometimes called the punctured Cantor tree. And there's a few ways to draw it, but one that I particularly like is we'll give it a hyperbolic metric so that the point at infinity of R2 becomes a cusp, and we'll draw that cusp down here at the bottom. Right, and then removing a Cantor set is the same as sort of making an infinitely branching tree, which is where the tree part of the Cantor tree name comes from. So, like, we kind of have these branches, and they keep branching off forever. Right, this is some infinitely branching doohickey. This is a highly symmetrical surface, and it's quite well studied, in particular by Juliette Bavard, which I will get into a little bit more in a minute. So there's this kind of special end down here, which sometimes gets called infinity, because if you think of this as the plane, this is the point at infinity. And, well, what can we do with this surface? Well, we can draw loops. So a loop is an embedded arc, so not self-intersecting. And what do I mean by arc? I just mean an embedded line with both of its ends limiting off to our special point at infinity. And of course we want to consider it up to isotopy because we're working with the mapping class group and we don't want wiggles to matter. So I'll draw some arcs. Here's one. That's an arc. It's a red arc. I'll draw a yellow arc. Maybe it goes up like that. Okay, and if you've dealt with mapping class groups before, you probably know what we're going to do next. The loop graph is a graph whose vertices are loops in the sense here. And we put edges between disjoint loops. Right, and of course secretly these loops are isotopy classes, so when I say disjoint loops, I mean loops with disjoint representatives. This is a graph. Okay, and then let's call it L of sigma. Again, this is for now at least, we're talking specifically about the punctured Cantor tree. So my first meaningful result is that the mapping class group is quasi-isometric to the loop graph. So I should say, to be clear, I did not define this loop graph, but I was able to show this quasi-isometry. Okay, so this is sort of an immediate answer to question 2 from before, right? This tells us, hey, we found a nice thing that it's quasi-symmetric to. And this is actually nice in more than one way. So first off, it's, you know, a graph with countably many vertices is already way better than this big uncountable monster that is the mapping class group. But it's even better than that. If you're a lazy mathematician, you always want to work with someone else's known results, and crucially, the person who really deserves credit, I think, for figuring out how important this loop graph is Julia Bavard, who showed that this guy is delta hyperbolic. So not just that the mapping class group is quasi-symmetric to some thing, right? But corollary, the mapping class group of the punctured Cantor tree is delta hyperbolic. And this is the first example, to my knowledge, of a mapping class group of any surface that is non-elementary hyperbolic. Non-elementary means there's two sort of cheating ways to be hyperbolic, right? One is to be bounded, quasi-symmetric to a point. Some big mapping class groups are quasi-symmetric to a point. The other one is to be quasi-symmetric to a line, so the mapping class group of the annulus is technically hyperbolic, but those are, you know, not the fun hyperbolic. This is a fun hyperbolic. And what's sort of cool about this theorem is then you can jump in and take all this hard work that other people have done. Not only is this hyperbolic, but Bavard and Walker have, to some extent, characterized its Gromov boundary. So we know what the boundary of this hyperbolic space is. Julia Bavard has a very recent preprint where she went into more detail, finding more points in that boundary. So this is really cool, in my opinion, and I appreciate how much sort of mileage you get out of this initial result. That said, the downside of this result is that it only applies to one surface, right? The plane minus the Cantor set. And it's not clear that this result can really be extended to too many other things because it really depends on the extreme simplicity and symmetry of that surface. But it might be possible to find something else if we let ourselves be a little bit more open to weirder graphs. You know, the loop graph is a kind of pretty canonical object, right? It's something that you could sort of imagine that people would naturally come up with, right? I'm now going to introduce an object which is less satisfying in that it's probably not something you would come up with unless you were trying to solve this problem, but it solves the problem very well. So first I'll need a definition. So we're no longer talking about the punctured Cantor tree, and the punctured Cantor tree will not fit this definition. So a surface is translatable if it admits a translation right? And my requirement of a translation is that it sort of shifts everything over. So I will define this by example. You can look in the preprint for careful definition, right? But what I basically mean is a surface that has something in it that gets repeated over and over again. So I'm imagining here's a surface which some other people have called this the Avenue of Chimneys, which I think is a nice name for it. Right, so here's a surface, and you can kind of think of this as being made of this little piece, and which I say little, it's still already infinite type, right? Repeated over and over again. So a translatable surface is one of these surfaces that's made of a little piece repeated over and over again. The piece itself can be as complicated as you like, but the repetition means that you could take this whole thing and kind of ka-chunk, shift it over one step, and that's what I call a translation. The crucial thing is that this really has to shift everything over, right? So every curve has to go off this way if you apply the translation a high enough positive number of times, and go off that way if you try to apply it a low enough negative number of times. Crucially, right, if you're familiar with n-periodic homeomorphisms, the translations are n-periodic, but a generic n-periodic homeomorphism will not be a translation because it only has to work in one direction, not in both. Okay, and a translatable surface naturally has kind of two ends that we especially care about, which I call E plus and E minus, right, which are just sort of the things that go if you all the way one way or all the way the other way. Okay, so what can we do with a translatable surface? Well, you can sort of see in this picture, right? There's a particular kind of subsurface, right, which is more interesting than others, right? If I cut this surface along these two curves, I get a subsurface that has this guy in it, right? And I'm being hand-wavy here because the details require a somewhat deep dive into the technical aspects of the Mann and Rafi classification, right? But let's just say there is a finite set of important subsurfaces. That we can sort of extract, thank you. There's a finite set of important subsurfaces of sigma that we can really extract just from the topology of sigma. There's no, this is a canonical construction, there's no choices that have to be made. That sort of put together tell you everything you need to know about the topology of sigma. I'm being hand-wavy here. I'm happy to explain the details in private. But trust me, you don't want to hear them right now. So what do we do with this? Well, we make a graph. The translatable curve graph, which I'll write TC as sigma, is the graph whose vertices are what? Curves. And by curves, I mean isotopy classes of simple closed curves, right? Curves separating E plus and E minus. So like these two yellow curves I've drawn here would be examples of curves that become vertices. and an edge between two curves if when you cut along those curves, you get one of these important subsurfaces. So you get something homomorphic to these, to an important subsurface, if they co-bound an important subsurface. Okay, so for our purposes, I know this is a little fuzzy because I haven't said what the important subsurfaces are, but we have some set of curves in some relation that gives us edges, and then of course you know what's coming next. Theorem. If sigma is translatable, then the mapping class group of sigma is quasi-symmetric to the translatable curve graph of sigma. And here, of course, the translatable curve graph is not, like the loop graph, is not something that someone else has studied a lot, so I'm working still on seeing what useful information can be extracted about translatable curve graphs, which would then apply back to the mapping class group. So as a final thing, you might think, okay, this is a pretty contrived definition. You've clearly built this thing so that it will work. Are you sure there isn't a better kind of geometric object that you could attach here, like there was with the loop graph, something that feels more natural? Well, no. At least not using curves. Okay, so my final theorem is if sigma is the mapping class group of sigma is quasi-symmetric to any graph. The only requirement about this graph is that it's built out of curves. So no requirements on the edge relation, no requirements on which curves. This could be a subgraph of the standard curve graph that we know and love, or it could be something weirder. If the mapping class group is quasi-symmetric to any graph whose vertices are curves, then sigma is translatable. And so, in fact, the translatable curve graph is the guide. You could make something else quasi-symmetric to the translatable curve graph. But the translatable surfaces with this translatable curve graph turn out to be the only game in town if you're interested in curves. If you're interested in loops, like the loop graph, that's still open. Again, there are rumors, I think there are things being done with that by people who are not me. And there might be reason to think that curves are not the right object to look at. Maybe you want to look at more interesting subsurfaces and the way that they intersect. But if you want sort of the simplest possible thing, which is curves, the only solution is translatable surfaces with their translatable curve graphs. All right. Please get in touch with me with questions. Get in touch with me if you have questions, and thank you very much.